So we've already started talking about the two types of hypotheses, and the first one is my null, which is that mu is equal to somebody's claim. And then the second one is the alternative. And the alternative could go one of three ways. It could either be less than the claim, or my alternative could be more than the claim, or my alternative could simply be just not the claim. And keep in mind that I could also write these in terms of the parameter p. And of course the only difference would be that we would be working with some percentages instead of probably a count, since the mean will probably be typically some whole number value. But the most common mistake is not doing this next piece, which is when we write our hypotheses, they must be in terms of the population parameter. So it must be in terms of either mu or p. And what students like to do is a no-no. They can never be in terms of either x bar or p hat. That is a major, major no-no. So notice I'm going to reuse this problem the 911 calls, and nothing's really changed except this time I want to state the null and alternative hypotheses. So for us, of course, the claim was that the mean time was 6.7 minutes. And I do want you to add one sentence in here that somehow didn't get put in, even though I intended it to. So add that sentence in there. Do the data provide evidence that the mean response time has improved? So this would lead me to an alternative. That sentence you'll see now is important, that the mean response time is actually less than 6.7 because it's improved. And in addition to writing it symbolically, for every hypothesis test you do, you must also write out what it says in words. So up here, the mean response time is 6.7 minutes. And down here, mean response time, we can word it a couple of ways. We can either say is less than 6 minutes, 6.7 that is, or we could say has improved, which would be the same thing. But regardless, as I already stated, you must put in words, both for me and for the AP test. Automatic deduction if you don't. So this next piece is a little tricky. It'll make sense the more we get involved in doing these problems. This, in the beginning, it'll be a little bit of a challenge to get your head wrapped around it. So a one-sided test is simply that my hypothesis is either a less than, we're going to do these in terms of mu, so even though we could do p. So either that I'm less than the claim or that I'm greater than the claim. And then these happen to have a kind of a nickname, I guess you would call it. This is called a left-tailed test, and the other one is called a right-tailed test. And you can usually tell because of the way the arrow is pointing. It'll make a little more sense here in a second also, because when I look at a left-tailed test, what's going to happen is I'm going to have my mu and standard deviation on here, and then I'm going to get an x bar, which is to the left, and I'm going to check, wow, how far out is that? Far out, man, far out. Versus over here on the right tail test, I'll have my mu and my standard deviation, and I'm going to get an x bar that's on the right. He's in the right tail, and so I want to know how far out in the right is he. Is that likely or very unlikely? Versus a two-sided test includes both tails, and this time notice I only have one option for the alternative, and that's that it's not equal to the claim. But what's going to happen is your x bar is either going to fall on the left or the right. Your sample has to fall somewhere. But what you're going to test is how unlikely is this or something similar to it. Now when I say similar, similar meaning this far away or farther. But I could be this far away just in the other direction. So that, and then same thing here, the sample mean happens to fall on the right, but I could be that far away also on the left. So that's really what the two-sided test is talking about. How likely is it that simply I'm that far away? Versus on the one-sided test, how likely is it that I'm that far away, but I must be on the right because I have to be bigger than? And over here, how likely is it that I'm this far away, but I must be on the left because I said the alternative had to be less than? The more you do these, the more it will make sense. So as we read the juicy pineapple problem, we notice that we have pineapples that are 31 ounces, and the growers are going to get a new irrigation system, and so they want to know how this change will affect the mean weight. Now, it's not very specific. Like, they're not saying that they think the new irrigation will make them grow bigger or smaller. So we don't know, which is what's going to lead us to just say fine, then we'll just do a not equal to, because we don't know if it's bigger or smaller. But the parameter that we're interested in is definitely the mean weight of our pineapples. And then when we have to write the hypotheses, so now I know the claim is that the mean weight is 31. In other words, we're checking to see, has anything changed? Did this irrigation system help or make it worse? Which means our alternative, again, since it was non-specific, is just that it's not that anymore. It either got better or worse. And so again, I have to write in words what I'm saying or what I'm talking about. And I got that actually from part A. And lots of times I actually just do this and then is not 31 ounces. So the second step of hypothesis testing is, oh my gosh, we cannot get away from this, checking our conditions. And I have an acronym that I didn't use with you yet, in case you're having a hard time remembering what they are, is that when you check conditions, you're committing a sin. So the S, of course, is for my favorite acronym, SRS. The I is for independence, but the way we verify that is through the population being greater than or equal to 10 times the sample size. Remember, our assumption of that is what allows the probabilities to essentially be independent. And then the N is for normality, and that'll be dependent upon whether or not I'm doing a means or a p-hat. Remember, the x-bars, you're using CLT, or mama is normal, and the p-hats, you're doing n times p-hat greater than or equal to 10, and n times 1 minus p-hat greater than or equal to 10. I'm sort of assuming that at this point in time, that's just like you have that memorized, whether or not you wanted to. It is now. So a test statistic, you need to look at your blue formula sheets, and this is also at the top of the boxes in section 3 that you've been using to not have to memorize your confidence interval formula. This is actually above confidence interval formula. So in order to find a test statistic, and in this case it's going to be either a Z or a t. Wonder if we've seen those letters before. But the formula is my estimate minus my parameter divided by the standard deviation of, just kidding, of the estimate. And so for means, I wonder which one we'll use. Which one? Oh yeah, t, because we've been using t on means. It's going to be x bar minus mu over standard deviation, which is s of x over square root of n. And for proportions, it will be z equals, and we'll have p hat minus p over the standard deviation. And in this particular scenario, we're actually going to have p because, of course, p is going to be our claim. So it won't be a problem. We'll actually have it now. So we can go back to using p inside the square root. So on this first problem, again, we're going back to the 911 calls, and I want to find the test statistic for the sample mean. So here I'd be using a t equals, and so I would have my estimate, which is 6.48, minus, remember my mu was 6.7, and my standard deviation for the sample was 2, and then the sample size was 400. So this ends up being approximately negative 2.2 versus on the example where my sample mean was 6.61, then I'm going to have the sample mean, which is 6.61, there's my sample, my estimate minus my parameter, which was 6.7, again over the standard deviation divided by the square root of n, the sample size, and this time I get negative 0.9. So our interpretation for the test statistic, for the first one, for letter I, little I, since our sample is now more than 2 standard deviations below the mean, we have good evidence that the population mean response time is less than 6.7, because that's pretty far out. But the second one is less than 1 standard deviation away. So since our sample mean is only 0.9 standard deviations below the mean, we can't really conclude the mean response time has changed. So you're probably starting to wonder, well, how far away is too far? How far away gives me good evidence? So if our test statistic is large, and we're going to talk about when is large enough, and in the direction of the alternative hypothesis, we have data that would be unlikely if that null hypothesis were true. And so we'll make unlikely more precise by calculating what's known as a p-value. And yep, here we go again with the letter p. Going to have another p to have to worry about, that being the p-value. And so this p-value